Okay. Get the microphone at the speaker. Hopefully this will work. X minus 5 equals plus or minus 7. Okay, because square root of 49, we're going to get positive negative 7. The last step is plus 5 to both sides, but we're going to do this new thing where we slide that in front and then write the plus or minus 7. I find that answer perfectly satisfying because we're going to have a lot of answers in this form. Some number plus or minus some other number that's not as easy to actually add to it, like the square root. In this case, we actually could finish, if you want, what is 5 plus 7? What is 5 minus 7?
2.
So there are the two answers. But let's look at the next one and then you'll see why this is actually where we stop lots of times. For the next one, we will again start doing regular algebra. Last operation first. Take off the 3. And then graciously, I didn't have a multiplier this time, so we'll go straight for the square root. This is where our simplifying radical skills come in, because we're going to have plus or minus the square root of 200. Well, how can we simplify the square root of 200? Well, it's 2 times 100. 100 is a square. Let's square it out. Square root it out, sorry. Plus or minus the 10. What does the 100 pop out as? A 10. What does the 2 do? It stays inside. Okay, we're almost done. One more. We're almost got x by itself. Oh, I forgot the step. It's minus 5 minus 5. So we put that in front, and then plus or minus 10 square root 2. Now there is no way to get more clear. That is both exact answers, because we have no way of combining a normal whole number like negative, or an integer technically, as like negative 5, with an irrational number like the square root of 2, which is some decimal that goes on forever. We could add them together approximately, but there's no way to add them together exactly, except writing it. By writing it like this, we are adding it together exactly. And this is the answer. This represents two numbers. One of the numbers is negative 5 plus 10 root 2. That is one. This is one number. This is how you express one special number. And then negative 5 minus 10 times the square root of 2. Here's the other answer. Some people put an or between them. Some people say and or, it doesn't matter. Both are answers, but only one is an answer, one is, I don't know. Last problem. Minus 16, x plus 5 squared equals 0. Square root both sides, and we get x plus 5 equals plus or minus the square root of 0. What's the square root of 0? 0. So I could just write a 0 over here. But I'm going to keep going with the pattern so that we get used to it. X, slide the minus 5 in front. X plus or minus the square root of 0, which is just negative 5. There's only one answer this time. Only one answer, but in terms of some sort of understanding of what drives quadratics, this would be thought of as a double answer, because there's two factors here. At the very beginning, right here, x plus 5 squared. In fact, I saw a couple of you try to multiply it out. That actually makes the problem more complicated. In this form, it's straightforward. There's only one square root to take. There's only one place x is. It's not like x squared plus more x, right? It's all just in one package. But there's some concept that there's a double root there. So this isn't for today, but just giving you a heads up for what's coming. This would be called like a double answer, because even though it's only one answer, it represents negative 5 plus and minus 0. So it's like, it's subtle. Okay. Leave your notes out, or leave your warm-up out, because we're going to take notes in a second. But at first, you don't have to take any notes. First, we're just going to have a discussion. We need to have a little talk, because as I alluded to earlier, there's kind of a scandal today. It's a little bit of a problem. Wow, it's out of focus. Alright, where this story begins is in your first concept of numbers. What was the first number you were told about?
Can we write this down?
No, this is just for discussion. Don't write anything yet.
Okay.
When you first learned that numbers exist, what kind of numbers were you told about? 1. And what else? 2. And 3. These are called the natural numbers or the counting numbers. They don't really tell you about 0 at first. But before long they tell you about 0, right? So if we put 0 on here as well, these are the whole numbers. And some people think the difference between whole numbers, natural numbers, that's not even that interesting. So let's not worry about it. But what did you learn next? Fractions. Yeah, they're like, surprise, there's a number in here. It's 1/2. And there's 1 and 1/4, right? You learned about these things. 2.5. 2.5 is a rational number. It can be represented as a fraction. So let's keep a list here. We have natural numbers. Then we have whole numbers that include 0, and who cares what the difference is. Then we have rational numbers. Those are fractions, anything that can be a ratio, including 3. 3 is technically a type of rational number because it's 3 to 1. Okay, where did we go from here? What did you learn about next? What about the rest of the number line? What's over here?
Negative.
The negative numbers. And maybe, at first they just focused on negative whole numbers. So -1, and -2, and -3. And those are the integers. But before long they're like, oh, there's negative fractions too. And so rational numbers encompass both positive rational numbers and negative rational numbers. And then at some point they're like, but pi is pretty cool, right? Pi, what's the deal with pi? It's like right next to 3, but it's weird because it can't be written down as a fraction. It can only be written down as an ever-expanding decimal that goes on forever without pattern or repeating. And that's kind of weird, but it's still kind of number. Does anybody know that numbers type? Irrational, not a ratio, can't be a ratio. And the square root, we ran into that this year with the square root of 2. Which is approximately 1.4. 1.41421. Square root of 2, you are right there-ish. It's on the line somewhere. Okay, and so now the number line is getting very dense. We filled it in with fractions, and in between every 2 fractions is another fraction, and in between every fraction is a bunch of irrational numbers, crazy decimals that are hard to talk about. The decimal numbers are hard to talk about, right? The irrational ones. But, they're important. I mean, pi is important, square root of 2 is important. We'll learn about another one this year, e. E is important. Here's the scandal. This is not all the numbers. There are way more numbers. And even worse than all of this progression. This progression's, it's okay. You learn a little bit more time and time again, but all of the numbers are on the number line. Guess where the next level of numbers are?
Off the number.
They're not even on the number line. They're in a cloud all around it. So what is going on with that? It has to do with, well, some of the topics we're talking about right now. So now you can take some notes. We're going to solve a problem. Ready? X squared equals negative 4. We need to find an answer to this question. What number, when you multiply it by itself, makes negative 4? Well, let's solve this algebraically. Let's take the square root of both sides. We'll find that number. It's got to be somewhere. The square root of x squared is x. And what is the square root of negative 4? Now you might think, oh, it's negative 2. But wait, what happens when you square negative 2? What is negative 2 times negative 2?
A positive.
Positive 4. So that's not what we're looking for. We're looking for some number that when you multiply it by itself, you get negative 4 as the answer. So then you might think, wait, negative 2 and positive 2. Because when you multiply negative 2 times positive 2, that's when you get negative 4. But that's not multiplying a number by itself. It has to be exactly itself when you square it. And doing negative 2 and positive 2, those are two different numbers. So that's not squaring. So let's just try to simplify this then. Let's say that the square root of negative 4 is equal to the square root of negative 1 times 4. Can we simplify this? What can we simplify out of this radical? Yes, Finn?
Negative 1 times 2 times 2.
Negative 1 times 2 times 2, and then the 2 can pop out, right? Or, in other words, the square root of 4 is 2. So let's do that. 2 times the square root of negative 1. Now that is a funny number. It kind of has changed our problem from what is the square root of negative 4 to basically what is this? What is the square root of negative 1? What is the number that when you multiply it by itself, you get negative 1? And the problem is this is a number. If you square it, you'll get negative 1. Where is this number? It's not on this number line. It's off to the side. It's out here in this cloud of other numbers that they keep secret from you until today. Today the lies end, and we get to learn about the square root of negative 1. Let's check though. Let's make sure that if we put this in for x, we'll get our negative 4 that we wanted. So we put in our number 2 square root negative 1, and we square it. And what will that be equal to? Well, the first thing we do is we write 2 copies because we're squaring something, so we multiply it by itself. Here's the number times itself. And now the kind of cool thing here is this is all multiplying. 2 times a thing times 2 times a thing. Well, if they're all multiplying, let's use the commutative property to put them organize them a little bit. 2 times 2, we know that's 4. At this point, someone might say the square root of negative 1 is that special number that when you multiply it by itself, you get negative 1. And then we are multiplying it by itself, and we get negative 1. Or someone else might say, well, I want to rewrite it like this. Square root of negative 1 squared, because we are multiplying it by itself. So we're squaring this weird number. And now I can see that the root and the square undo each other, and I have 4 times negative 1. And what is 4 times negative 1? Negative 4. That's where we started, when we took the square root of negative 4. We got this weird number, and now we squared it, we're back. So we have discovered a new flavor of number. Nice. Okay, here's the problem though. We have been doing math on number lines, and for a long time, people would do math on a number line like this. And they would say, okay, here's a number 2, and I want some rule that'll take that number and subtract 5. What will be the answer? They'd queue up another number line. Okay, what is 2 minus 5? Negative 3. Okay, perfect. What about some other number? How about positive 3? Put a different kind of dot, I guess. And then we'll map that, 8 minus 5. to this location. And they're like, let's try 4. Let's put a box around 4 so we don't get confused. 4 minus 5 is negative 1. And they did this for a while until someone named Descartes came along 400 years ago and they said, hey, you got 2 number lines here, right? Put one number line like this. 0, 1, 2, 3. And put the other number line like this. Yeah, this is the Cartesian plane. If you've ever heard it called the Cartesian plane, it's named after Descartes. And now, see this relationship? 2, but applying our rule spits out negative 3. Now we can represent that with one dot. This dot represents both the 2 and the negative 3. And you guys, well, I'm not on the screen. This dot represents both the 2 and the negative 3. And you guys have known this because you write it down as 2 comma negative 3. This dot is 2 things. Okay? But this setup, where you put 2 regular number lines next to each other, doesn't account for this new number we have. There's no space for it. So to make space for it, you have to ditch one of them, go back to a normal number line. 0, 1, 2, 3. And now our new number is up here. The unit is the square root of negative 1. That's the new number. Down here is negative square root of negative 1. And negative 2 square root of negative 1. And 2 square root of negative 1. Up and down this axis. Now, this looks almost exactly like it did a second ago, but it's totally different. Because now, if I put a dot here, this is not 2 numbers anymore. This is 1 number. It is 3 with also some flavor of negative 2 square root of negative 1. So that's kind of hard to get used to. We need 2 dimensions to talk about one number. We need 2 dimensions to talk about one number. What would we need to do in order to do this trick where you have like one spot that refers to 2 things? When we had number lines, we had 1 dimension, one back and forth. That's 1 dimension, back and forth. We added another 1 dimension, and we could do our trick. But now we start with 2 dimensions just for one number. How many dimensions are we going to need to do our relationship trick? We relate one 2-dimensional number to another 2-dimensional number. How many dimensions will we need altogether? 4 dimensions. How many dimensions are there to play with?
3 dimensions.
3D. We live in a 3-dimensional world. That's not enough dimensions. So it gets very hard to talk about these numbers. And that's why we save it for Algebra 2. It gets very complicated. These are called the complex numbers. You can't even draw a picture of a function. You know, all those functions you know, linear functions, exponential functions, quadratic functions. You can't even draw a picture of a complex function because there's not enough dimensions. So it gets hard to think about. But we can do it. We can first of all make it a little bit easier. We don't have to keep writing the square root of negative 1. We'll come up with a whole new symbol that we'll use to explain this stuff. And you can use colors. So if you use all 3 dimensions and color code the function, then you can use color as your 4th dimension. So there's different ways of looking at it. Let me see if I forgot anything in my notes. I guess the only thing I'll mention is we're going to talk about this question next. Where does this parabola equal 0? We want to know where the x-intercepts are, or the roots or the factors of the quadratic. And right now, it doesn't look like it crosses 0, but that's because we don't have all our dimensions down. I'm going to play a little video for you. How are we doing on time? Oh, got plenty of time. Okay, so because the numbers, these new numbers, are not on the number line, but off to the side. For almost 200 years, people did not believe they existed, even though they were using them in math. They would solve problems. These numbers showed up in math. When they started studying quadratics, they started using them, and they started saying these aren't even real numbers, because they're not on our number line. They hadn't realized that they were real numbers. So they gave them a terrible name. Timothy, what name did they give him?
Imaginary numbers.
Imaginary numbers. It is really frustrating because it's hard to think about something that's imaginary. But there is one nice thing about using calling them imaginary numbers. I would call them complex numbers to the greatest extent possible, because like this dot I've drawn down here is a complex number. It has a real part and a quote-unquote imaginary part. But for numbers that are just on this axis where their real part is 0 and they only have an imaginary part, people don't like to call those complex numbers because they're purely quote-unquote imaginary. But it does give us a letter to use. Instead of writing the square root of -1 over and over, what letter could we write? We could write a fancy I. So this is our new number. This is the symbol for our new number. It's this symbol, fancy I. And you can have 2 fancy I, and you can go off, and over here, this location over here that we found earlier is 3 and also -2 fancy I amounts. This is one number. A new complicated number, a complex number. Okay, here we go. Story time.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis, so according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power or degree of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention.
This subject has hitherto been surrounded by mysterious obscurity. It is to be attributed largely to an ill-adapted notation. If, for example, +1, -1, and the square root of -1 had been called direct, inverse, and lateral units instead of positive, negative, and imaginary, or even impossible, such an obscurity would have been out of the question.
So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral, so from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions by going way back to the discovery of imaginary numbers.
Remember when hold on, we got 3 minutes. Remember when he said he was going to call them lateral numbers for the rest of the video, and then he totally forgot about that immediately? That is how hard it is to not call them imaginary numbers, because that's been their name for 400 years. They play a critical role in electrical circuits. Every 3D video game you've ever played, you can kind of imagine how a number with more dimensions might help you make a video game with more dimensions, and they're how we make fractals. So quote-unquote imaginary numbers are real things that we use to do things every day, and I will try my best to call them complex numbers. I might occasionally accidentally call them imaginary numbers. Okay, that's a lot of excitement for the day, learning about a whole new dimension of numbers, so let's celebrate by going a minute early, 49.
Hey, sir. Want to see something cool? My own map of a man